So just rewrite out your stoichiometry table. This takes into account the fact that you're now saturated in the vapor phase, so anything new formed, so this is going to stay constant, and any new B that's formed goes into the liquid phase. So then you can solve for FT. So if you just rearrange this, you get Ft is equal to Fa naught times 1 minus x over 1 minus yb. Then this would also change your volumetric flow rate. So now you know Ft is equal to this, and your Ft naught is equal to Fa naught. So you plug those in for here, plug those in over here, and you get V is equal to E naught times yeah.
I'm so confused as to why you're not making,
As to why you're not what?
like, there's no change in.
So there's no change in, so this is pretty much just for the gas phase. So there's no change in B because you have a saturated vapor, because you're over the vapor pressure, and any new species B that's formed isn't going into the gas phase because it's saturated, it's being formed as a liquid.
Okay.
And yeah, so just condensing as a liquid. So you are forming more B, it's just not in the vapor phase.
But in this case, we don't care about the phase? Or
No, I think you can pretty much ignore the liquid phase once you take into account that it's there and work around it. So.
What was subscript for F on the bottom right?
The bottom right, over here.
No.
Oh, so this is Ft and this is Ft naught. So the total flow divided by the initial total flow. So the initial total flow, since it's pure A entering, is just Fa naught. And then Ft is changing according to this equation up here.
What are we trying to solve for right now?
So this is you're calculating the conversion and the reactor volume again, just at a different feed pressure. So the conversion's staying the same because the energy balance really hasn't changed. None of the parameters have changed, so the conversion is still going to be 0.83. I'll write that down. But you're essentially just solving for a new reactor volume. Now that there is, taking into account that there's condensation of B and you have a saturated vapor phase. And you know that you're from idle gas law again, your V naught is now, I think it's 15. Yeah, 15 liters per second. So now that you know your CA, you can just go ahead and plug that back in for your mass balance. Or you could go ahead and calculate it here, or you could plug it back into your mass balance and do it there. But you know your design equation is still this. So now that you have, you know your YB is, your YB is 0.5 because from route solve pretty much. It's just the vapor pressure over the total pressure. So it's 0.5. You know, FA naught still, T naught, your V naught you can recalculate using idle gas law. You know your T is still 350. So this gives you a CA of 0.17. Moles per liter. And then when you plug in the 0.17 for CA, you can read your K is going to stay the same. It's still going to be the 6.6 times 10 to the negative 2. You know your FA naught, and you know X is still 0.83 because your energy balance hasn't changed. And you get that your new reactor volume is going to be 222 liters. And considering the last one was much larger, you can see that by just raising the temperature or the pressure, you know, from 2 to 10 bar and condensing some of the liquid phase, yeah, the last one was 1.9 times 10 to the 3rd. So you can use a much smaller reactor for the same conversion at the same operating temperatures. So that was the first problem. So the only real tricky part about that was just realizing that there's condensation going on. So you have a phase change. So does everyone have this?
Would you know if Professor Hibbets would include phase change in this test? Because it's supposed to be for the first test.
Yeah, I mean, I think everything's kind of cumulative in this course, more or less. It's like you still have to use rate equations, still have to do design equations. So I don't think it's off limits. I don't think he used planning to be that mean. So I doubt it, but it could be. You guys had like what, one lecture on it, and it's not in the book?
This is the second question.
Yeah. Yeah, so probably not. I think Weaver might have spent a little bit more time on it. So the next problem was on multiple reactions, since it was also fair game because that wasn't part of the first test. So it's a batch reactor, it's isothermal. So it's liquid phase and is charged with equal molar parts of A and B. And they give you the initial concentration of A is 1 mole per liter. And then you want to maximize B, or want to maximize species R with respect to A. So yield of R. Sorry, yield of species R. So the first part of this question was also nice because it kind of like lays out everything we need to do in steps and just asks in parts. So the first part was just express the species balance equations in terms of species concentrations and rate coefficients using time as the independent variable. And the rate of each reaction is given by an elementary rate law. So all you have to do is